Yeah. I restarted. Well, they're just not emphasizing. Yes, the sources for it.
I went through magnetic fusion general and the efficiency of it, feasibility of it, and then the conclusion was like.
Yeah, you basically just whichever method breaks that's what it's serious. Yeah, do you know what actually would be clever idea? Not necessarily.
Okay, welcome everybody. Today is the week 9. We have one more lecture to conclude the material. And so last week, today is the second lecture about BJTs. Last week we looked at how we can DC bias properly a BJT. We've seen effectively 3 configurations, all in common emitter, what we call common emitter configuration. We've seen how to use the fundamental equations of the BJT to do that. And all that was about placing this nonlinear component in a specific operating point that we called, if you remember, we call the quiescent point. And effectively, I feel today like everything we did up until today was to reach this moment. Because today we are going to use the BJT as an amplifier. And so we are going to see how now the BJT DC biased properly to operate at a quiescent point Q can now be used to amplify things, either a voltage amplifier or a current amplifier. And so we will go again over these 3 configurations we've seen last week, which was, if I remember you, all were common emitter. The first one was called, we called it C1 fixed bias. The other one was C2 emitter bias. And the other one was C3 voltage divider. And so we will use this again today, but looking at them, or maybe showing you how to look at them in the AC regime as now small signal amplifiers. So let me see if I'm forgetting anything in my opening statement. Oh, well, the only thing I would like to add is, remember, the common emitter we are focusing on is just one of the many modes the BJT can be operated in. Remember, we are not dealing with the other modes just because the common emitter is the, let's say, the most useful for the things we may be wanting to do. But remember, there is also the common base and common collector. So we are not dealing with this in here, but just know that they exist. So okay, let's start. So to be able to understand how the BJT can be used as an amplifier, we need to linearize it. And the way to linearize it is to consider very small AC signals. This is the method, one of the many methods we've seen, the 2 or 3 methods we've seen of linearizing nonlinear component is the so-called small signal method. So we will apply that here around the quiescent point. So the aim is to show how we can linearize this nonlinear component around the quiescent point, and then we demonstrated that this can actually be used to create amplifiers. So the first thing to realize is that the BJT, which I shall remind you, has this symbol. This is the collector, the emitter. Remember, we know we will always be dealing with the NPN BJT transistor. We've done this last week. We will keep doing the same for the weeks to come. Remember that everything we say holds true also for the PNP transistor. Simply remember what we said, that you need to change the signs to currents and voltages. So we stick with the NPN. This is the base. So this is a 3-terminal component, and this 3-terminal component can be seen as a 2-port element. 2-port in the sense. So imagine, I shall draw it probably here. So you could imagine this is inside a box. And so you have base, emitter, collector, emitter. You see that the emitter here is common. So this is a 2-port element for the common emitter configuration. So I can see my BJT as a 2-port circuit, input port, output port. We've defined, I think in lecture 1, what is a port. A port is 2 terminals of an electronic circuit where you can attach something, a generator, something, okay? Port, output port, for example, input port. So this is for the common emitter configuration. We see that the emitter here appears everywhere. So that's why it's the common emitter view, let's say. There are other, obviously, ways to see the same thing, which would be corresponding to the common base. I mean, I could make a drawing here of how to see the common base as a 2-port. So this is the emitter, this is the base, this is also the base, and this is the collector. This could be the input port and the output port, and vice versa. I mean, it doesn't really matter now the name. This is for the common base. So a 2-port element made by BJT in common base configuration. And just to complete this, since we have started now, we could do the common collector, which could be this one here. This is the collector, the base, the collector, the emitter. The collector is common, so input, output. And this is the common collector, 2-port common collector configuration. So today, and for the end of the course, we will deal with this. We will think of our BJT as a 2-port element in common emitter configuration. Okay, so let's talk about then the AC small signal model. How do we apply it? So as I was anticipating previously, we know now everything, or we should know, on how we can bias this device properly to place it in a specific quiescent point. Quiescent point means we know how to define precisely the base current, the DC base current, the DC base voltage, the DC collector current. We've done it last week. We've defined ways on how that could be easily done. So that's solved. We know how to place this in a specific quiescent point. So now the idea is to linearize this nonlinear component just around the quiescent point. Just for those of you that are if you want to have a look at, this AC small signal model with the idea, the principle, we've done it before. So we did it in chapter 1 when we introduced the concept. So go to chapter 1 when we talked about nonlinear circuit analysis. And we did it also in chapter 3 when we were talking about the PN junction. We introduced the concept of diffusion capacitance, and together with that, we talked also about differential resistance and so on. And there I've also talked about the difference between differential resistance and DC resistance. So just so you remember, if you wanted to go back and have a look, similar concepts that we will discuss today, or maybe related, are there. So what are we going to do now? So up until now, let's pick here we have, this is VB, isn't it? And here we have IB. So now what we want to do, we've dealt with VB, or all the other quantities, as DC quantities, constant. Now what we want to do is to add to these quantities a little AC signal on top. So we will assume that all these quantities now have a DC part plus a small AC part. That's where the small AC signal model comes in. So for example, for VB, I will not be dealing anymore with VB and a DC signal. Now VB, in general, as a signal, is a function of time because it's made of two parts. VB, which is the DC part, plus VB, according to the formulas we've been using, I would write it like that. This is an AC signal in time, which is, for example, a sinusoid or a cosinusoid, whatever. So with this new approach, I will use this notation to say this is a signal that varies in time and is made by a constant value, that is the DC part, which is defined by the quiescent point, the DC analysis we did last week, plus now a small signal we will add on it, which is AC, purely AC. So if I wanted to represent these things let me do in red. This is the AC part. This was the DC part. And so the total now, which is that one, so that's what I'm planning to do now. So effectively, we will superimpose to everything we did last week a new layer. The layer that will deal with the eventual AC part of the AC component, let's say, of all these electronic signals, either voltages or currents. So in this new way of approaching this two-port system, I should add here, to be precise, T. And also here, this is VCE T now, and this is IC T. And so I could, if I wanted to put everything very explicitly down, I could write it. You see now that in these two ports, everything that will happen is described by the four variables: VB, T, IB, IC, and VC. So these are the four variables I will now start dealing with, because my two-port is completely defined by these quantities. These are the only things that I see from outside. Okay? So, based on this new, let's say, this additional layer I want to add to my approach, let us write down all the four quantities here. Would be VBT is, as we did there, VBE plus VB tilde T. Then we have IB T is IB, this is the DC part, plus IB tilde T, this is the AC component. And then we have VCE T will be VCE plus VCE tilde. And finally, IC will be IC plus IC tilde T. What do these four quantities here represent? First of all, are these AC or DC, according to what we've said? These are all DC. How did we call these last week? What do they define? These four DC quantities. We've said it even a few minutes ago. It's this weird term. These four quantities define the quiescent point, where my operation, my BJT is operating precisely. So all these we know how to deal with. We've done this last week. The question is now, so we know how to, when I'm presented with a common emitter circuit, one of the ones that we've seen last week, and I'm asked define the quiescent point, effectively, I know how to deal with that problem, and what I'm doing, I'm defining effectively these quantities. So now, so that's, let's say, dealt with. We know how to deal with that. The question now, how do I deal with this? Well, how do I treat that in such a way that I'm effectively dealing with this? That's the question that we will try to answer today. Okay, this is referred to the DC part. We've done that. This is in the AC world. So we need to now and realize, how do I need to look at this to properly analyze the eventual circuits I will have to deal with, but in order to address these quantities, the AC parts of these signals. So we have four variables here. There are, at this point, this is where now the model will kick in. We will define it. Now, the approach here with four variables is we pick two as independent variables, and automatically the other two will be defined, because this is voltage and current. So I could pick two of them that act as independent variables. The other two are dependent from the rest. And so I could then, we will see in a moment, use that to linearize the circuit. Depending on which two variables of these four I pick, the model takes a different name. Okay. Now the one we will use, which is the one that probably is most widely used also in the books, most of the books, is the so-called hybrid model. So we will deal with the so-called hybrid model. Hybrid because here we have voltages and currents. Can you guess why this will be called hybrid? We will pick one voltage and one current. Okay, and we will pick actually one quantity from the input port and one from the output. And in the hybrid model, what we pick as independent variables is IB, how original. We've said that IB is very important, isn't it? So we will pick IB as our important signal, independent, and VCE. Okay, so in the hybrid model, we assume that these two act as independent variable. And so automatically, we can I thought the camera was automatically we can we realize the rest has to be a function of these quantities. If we are assuming that these two are independent variables, then we should agree that isn't it? And the same for the other one. I see. Will also be a function of these are heavily nonlinear relationships in general. Maybe we don't even know these relationships if I wanted to analytically write them down. Or maybe we do. The thing is, we don't care, as we will see in a moment. Okay? Now, the thing is, we will try now to linearize this because we are using small AC signals. So let us have a look at how we will do that. Before we move on, though, we need to remember effectively that VB is on the input port. So whatever we will do here effectively will be telling us how the input port looks like. This instead relates to the output port. So this part will tell us, once we linearize it, how the equivalent circuit of the output port should look like. Overall, together, we'll define the hybrid model, which is a linear version of my nonlinear component that suits its operation for small signals. Okay, that's the overall picture, the overall idea. So how do I linearize this? We use Taylor expansion, probably something you've done millions of times now. And so the idea is, imagine that I have a function y f x, and I'm considering now a point x prime that is x plus delta x, which corresponds to y prime f x y x prime. If I wanted to avoid using f, which is heavily nonlinear, for example, I could Taylor expand f around, let's call this x0. So I could Taylor expand f around x0, and what I would write is, according to Taylor's theorem, is f x0 plus df dx calculated in x0 plus, time x prime minus x0. And x prime minus x0, according to my initial starting assumption, is effectively delta x. And now I realize that epsilon prime, my expectation is that epsilon prime will be epsilon 0 plus a certain delta, isn't it? That's what I expect. I'm introducing a small perturbation here. I'm expecting a small perturbation there. And so what we can already anticipate is that, you see, epsilon 0 is actually this one, isn't it, according to the definition. So if I look at this chain of equalities, epsilon 0 actually can be eliminated, and you are left effectively with this. I mean, we are discovering the wheel, something you obviously should know probably, is that and so with applying this very simple principle of Taylor expanding around a certain point, this x0 for us serves as the quiescent point. Is the point where the system is operating. And I am expanding the nonlinear functions that represents its operation just around that little point, and becomes a linear relationship. This is a number, the derivative around x0 is a number. And so this is a linear relation now between any small perturbation around the quiescent point, which will result in a certain output, delta y. And that's what I'll do now. Does this make sense? The perturbation for us, the delta x, is for us a small AC signal. Is there any issue with this chain of thinking, let's say? So I'll remove this and now try to apply that to what we've done. So this is the thinking behind. And now we'll put it in practice on those. So I will start from this. You see, VBT is that, but is also this. So what I will start writing is that VBT, which is equal to VB. Let me make it explicit. This is the quiescent point, the DC part, defined by the quiescent point, plus the small AC signal. But this is equal to that. VB, IB, BC, T. Probably I can remove this. We now got the point. So we want to expand. You see that here we have, this is the IBT and BCT are the quiescent point values plus a small perturbation, a small AC signal on top. And so I need to now expand effectively this function VB around those quiescent point values. I use again Taylor, and so this will become VB at, instead of having IBT, which is the full signal, I used only the DC part. I neglect the small AC. This is the quiescent point. This is telling you I am expanding around the quiescent point. Plus, now the derivatives. Now I need to put the derivative of VB toward the first variable, IB, calculated in the quiescent point, time the delta related to IB. So I need to write IB T minus the IB at the point where I'm doing the expansion, which is IBQ. on node. I shouldn't have deleted that. But IBT minus IBQ, which is the DC component, is effectively the AC part. We said that IBT is IB, the DC part, which now we are indicating specifically with Q, plus AB tilde, the AC component. So IB minus that is IB tilde. So this quantity here is actually the AC signal. That's magic. So that's actually the AC signal that we have now introduced into the process. Plus, I need to add another derivative to ward against another variable. So dVBE, dVCE, calculated in the quiescent point, time, same story, VCT, the actual signal, minus the point at which I'm doing the expansion. For VCE is VCQ. And again, this is actually VCE tilde, VCE, the small AC signal. Okay, now, as I briefly mentioned previously in that initial part with Y and X, you can see that by definition, VBQ, the DC part, VBQ, is actually represented by this quantity. It comes from here. If IB is just a DC quantity and VCE is just a DC quantity, then this is give you VB, which is just a DC quantity. And this is represented by this quantity here and that quantity there. So effectively, I can, if in my mind I'm thinking of looking at this part of the chain of equalities and all this, okay? I'm thinking of this equality now. So by looking at this equality, I can get rid of these two terms. These are the same, I can remove them. By definition. And so that's exactly where I wanted to be now. I have something that is a linear combination of quantities involving only the AC signals. I'm building now the model. So I will need lot of space actually now. So I will get rid of these. Actually, I can write this, for this equation here, I can write it down here. So I can write VB tilde equal to, let's start introducing some names. This quantity here is dVB over dIB. These are both quantities that relate to the input port, VB and IT. This is a derivative though. So this is what we would call the differential resistance of the B junction. Remember that B is a junction, is a PN junction. So dVB over dIB is effectively what we called, when we did it in chapter 3, the differential resistance of the B junction. This has a name, is indicated as HIE. The I stands for input, because remember, we are looking at this as the input of this port. So is the differential resistance of the B junction, and we indicated with the HI. E stands for a common emitter, because all this we are doing is for the common emitter. So just to remind ourselves that this parameter relates to the common emitter configuration, we always put an E at the end. So with HIE, we intend this differential resistance. So this is a resistance, is measured in ohm, okay? Generally, this is of the order of around 1 kilo ohm. So, HIE time IB tilde T. And then we have another term, that is this one here. The VB over the VCE. These are the two voltages, one in the input, one in the output. So this is the derivative of their ratio. Well, the ratio, the derivative of the ratio. And generally, when you see voltage divided by voltage, you immediately think of something that tells you a voltage gain. This is the so-called reverse, I don't want to get it wrong, the differential reverse voltage gain. Reverse because it's the voltage in input divided by the voltage in output. So differential reverse voltage gain, and is indicated by HRE. R for reverse, E for common emitter. And so this is obviously adimensional because it's voltage over voltage. It's generally very small, around 10 to the minus 4. Okay, we will make a table at the end with all these values. HRE times VC. And I will remove everything now, in this part. So you can imagine now that I can do exactly the same for this. So I want to do exactly, in the same level of detail. There is no reason. We now got the point. Let me just write the final result. So this will be, I will still write down the derivatives so that we can comment what they are. So this is the, you can find anyway all the steps on my notes, but it's exactly the same. So DIC over DIB, calculated in the equation point, time IB tilde T, plus DIB dVCE, calculated in the equation point, time VC. And now, this first term is the derivative of the ratio between IC and IB. So this is the differential current gain forward, because it's output, IC is in output, IB is in input. So this is indicated as HFE, forward for the emitter configuration. And the other one here, this one, is a current divided by a voltage. So this immediately is the inverse of a resistance, is a conductance or an admittance, if you want to look at it from the impedance point of view. So this is indicated as HOE, output, because it relates to the output port, is related to IC, so it's related to the output port, and represents conductance, okay? We will see in a moment the value. I think, if I remember well, this is quite small, around 10 to the minus 6. So in the end, I will replace this value here so we have the nice equations all together. Ta-da! A linear model of, for the analysis of my BJT circuit just for small AC signals, remember. And I should stress small. It's very important that they are small, because otherwise this Taylor expansion to the first order is not really valid. Do you understand that? Oh, obviously we should stress also some things. So HFE, we said is the differential current gain, forward current gain. We've seen last week something about current gain, haven't we? We've seen last week that, I mean, we didn't go through the analytical demonstration, but we did say, look, we did qualitatively explain that in the DC regime of my BJT transistor, IC is much, much bigger than IB, and actually we can demonstrate that they are proportional. So beta is effectively an amplification factor. Current amplification, we called it. Last week we can't remember the exact wording, but something like that. Now we see again another, in the AC regime, there is again a current amplification factor that now is called differently because it comes through a different route. How much do you think this can be? It must be around beta. Okay, don't be surprised that that is very close to that. Okay, if beta is the amplification when I'm in the DC regime and now I'm tweaking a little bit IB, also IC will be tweaked by the same amount, beta, effectively. So don't be surprised by the fact that effectively HFE is roughly equal to beta. Okay, so let me clean up this board. So how do we translate now? So this model is very nice, all very beautiful, but now we need a circuit. We need an equivalent circuit, as we did for the, I don't know, think of the PN junction. In the end, we needed an equivalent circuit with a piecewise linear approximation, you remember. So in the end, to be able to use these things, we need a circuit. So putting everything together, the hybrid model, these couple of equations are suggesting us this. Maybe I shouldn't have removed that. Anyway. Yeah, probably I should do it here a bit smaller. So this is B, E, C, E. So these two equations are suggesting us. So let us have a look at this one first. We said this is telling us something about the input port. So something about this part of the two-port system. So dB, which is the potential across these two terminals, is a resistor time IB. IB is coming in here, remember? Plus a voltage. Isn't it represented by these two things? A resistor where IB is passing through, plus a voltage, a power supply, if you like, a generator, which is obviously given by HRE DC, according to that. So I've drawn the input part of my model. Now I'm doing the other part, so related to this equation. So this equation, what is suggesting? It's suggesting that IC is given by, this is a current. We said this is a dimensional, it's a current amplification, differential current amplification. So this is a current. So this is represents a current generator present in the circuit. We will discuss in a moment why it's like that. And then there is another term. This is the inverse of a resistor or a conductance time a voltage. The voltage in output. So there is the voltage in output is fully seen by this resistor. How should I put the resistor in such a way that the resistor sees VC in full? This is the hybrid model, the equivalent circuit of my nonlinear component using just a couple of resistors and a couple of generators. It's completely linear. This generator is pointing in that direction because IC is going in like that according to the formalism we've been using. And so this current has to continue like that because you see this term is positive. So the current has to continue in that direction. And this resistor, or well, HOE, remember, we said is a conductance, so is the inverse of our resistance as value, HOE. But has to be placed like that because of the way it appears on here. Because HOE, you see, this is a current. This is the current that is flowing through a resistor that has applied to its terminals VCE. And that's the only way it can be. The current that is flowing through here is representing this term. So, please note, you see here I still kept T in my formalism, just because these are AC signals, are sinusoids, cosinusoids, whatever. Obviously, now we are adults, we know how to treat these things, we can drop T and think just about the phasors. I could drop T from these equations, and these are IC tilde is the phasor of IC, which contains information about the amplitude and eventually the phase. So that's why in the model I'm not putting T anymore. I'm just putting IB tilde, VBE tilde without the T anymore. I'm now thinking just at the phasors, so the amplitude of these quantities. And an equivalent way, so let me just remove just I don't want to create, we now understood that this was represented by that. Okay, so that's the model. We could redraw it in a completely equivalent way, just indicating the way we wire the emitter in a just slightly different way. Just so you see that it's still a three-terminal. Let's say this is more two-port. This is also two-port, but also is now three-terminal again. I'm not writing again these things, it's obvious, the same number. So this is our beautiful now model. And here comes the simplification, because this is simple, but we want to make it even simpler. We are not happy. We want to make the star a dot. We want to make the car a point. So we want to make it even simpler. And the reason is this, is that, as I said, let's write down the values. HFE, HOE. So HIE more or less is of the order of 1 kilo ohm. HRE is an adimensional number, is roughly 10 to the minus 4. HFE, as we said, is, let's say, around 100. It's beta, adimensional. And this is, we said, is a conductance. It's 10 to the minus 6 Siemens. So that 1 over HOE, which is a resistance, is around 10 to the 6 ohm. So what I see here is that HRE, it seems to me quite small. HOE, or the resistance, 10 to the 6 ohm, it sounds relatively big. And these are the two quantities now I want to focus on to remove them. I will finish this and then we have a break. So first of all, HRE is appearing in my model, in my equations, here, in the input part, and is multiplied by the AC signal VCE, is this term here. Now VCE is the, let's focus just on the amplitude. So VCE as a signal, as an amplitude, how much, because we said that we need to focus into small signals. So how small is small? So let's take it the other way around. The DC biases we've been dealing with last week relating to VCE, how big was VCE? We said a good choice always is to take VCE equal to VCC over 2. VCC is the power supply voltage. So if VCC was 15 volts, the half of that would be 7.5 volts. Okay, this is related to the DC analysis. So in DC terms, VCE is around 7.5 volts. How much would you allow that to change? This perturbation, this VCE tilde. Can I say 1 volt? Maybe it's even too much. I would say even less than that. So in this optic, from this point of view, HRE time, say 1 volt, is 10 to the minus 4 times 1 volt is 10 to the minus 4 volts. It's 0.1 millivolts. So that really is something that is very, very small. Okay, so I'm really tempted to say, I will forget about this. The other thing is HOE. So this resistor here has 1 over HOE, which is the resistance, is 1 mega ohm. So the 1 mega ohm is not a huge resistor, but is also not very small, isn't it? We generally deal with resistors as we've seen last week. If you remember when we did the analysis of the DC biasing and so on and so forth. And the resistors we dealt with were in the order of kilo ohm. Okay, so this is definitely much bigger than that. First thing. Second thing, in these equations, HOE appears on the output multiplied by VCE. So this is a current. HOE is 10 to the minus 6 time, as we said, let's say VCE will be 1 volt maximum. So the current corresponding to this is 1 microamp. Okay, 1 microamp. Normally, the output of the amplifiers we will be dealing with, the IC part, the IC in the AC regime, this quantity is generally in the order of hundreds of microamps, or even millions, or even tens of milliamps. So this quantity I can actually forget about that. And so the reality is we will always be, just to simplify things, we will always be using a simplified version of this model, which is effectively only containing this and that. And so we are effectively going to throw out this term and this term. And the corresponding model will be simply be aware, though, of the assumptions we are making and the numbers we have roughly calculated to make these assumptions. Okay, so this is our simplified hybrid model. And so we will be sticking to just these relations throughout. Whatever we will do, IC tilde is HFEIB, and DB is HIEIB. We will keep using these things from this point onward. Everything we've done here in this model, remember, relates to AC small signals, but also we need to add one thing, low frequency. Low frequency means, let's say, below or up to 1 megahertz. We will see at the end of the other hour, the next hour, well, I don't know if we manage, just for curiosity, what may happen at high frequencies. Okay, so we stop here and we have a 10-minute break, and I'll see you at 3:10.
That's very good.